Okay, so on with thermodynamics. Dun, dun, dun. So thermodynamics are all about kind of tracking thermal energy or tracking just energy in general, okay? And energy is one of those things in this universe, I would think any other universe, the multiverse theory, that energy is one of those things that's conserved. So you can track it, and actually energy can be and has been converted into matter. Way back when, at the time of the Big Bang, a lot of energy made a little bit of matter. But in general, energy is conserved in this universe, especially conserved here in southeast Iowa, our neck of the woods. So we're going to be doing problems where we track energy when physical processes occur. Now, when it says physical processes, I'll go ahead and start setting you up. That's basically usually phase changes. You know, something melts, something freezes. Energy is exchanged, okay? And chemical processes. Some things actually, when a reaction occurs, it releases a lot of heat, okay? And sometimes when a reaction occurs, it needs heat to occur. Okay, so energy is always going to be conserved. So I'm going to draw a little picture down here at the bottom. I've been enjoying some of you guys' pictures. Are just awesome, okay? So we do a lot of things in beakers around here. So I'm actually going to draw a beaker. And inside my beaker, I'm going to draw my famous fluid inside my beaker. Okay. So if we had a reaction, I'll put RXN for reaction occurring inside there. Do you buy this? That actually this thing that I'm circling, that would be our system. Or what's inside that red circle, that would be our system. If that's a reaction occurring. The beaker would be, I'll put it in green here, the beaker would be our boundary. And then everything outside the green would be our surroundings. Okay, so that's kind of what we have going on. And so we have the system of interest. It could be a beaker, it could be something else. And then we have the boundary and then the surroundings. Okay. So if we have an isolated system, an isolated beaker, what does that mean? Well, it could mean a few things. But you think the word isolated means kind of set aside. And so in the broadest terms, it means that it's set aside and that glass or whatever is going to contain all the mass and all the energy is going to be contained in the system. It's not going to cross the boundary. Isolated. Isolated system, closed system, you know, those can be actually oftentimes used synonymously. Sometimes there's kind of a little nuance to the whole isolated system versus closed system. And if there is, the closed system is where mass doesn't go across the boundary, and the isolated system is where energy does not go across the boundary. Now I'm going to switch gears here in a minute. Now, as I've been kind of saying my little stuff in my beaker, like this is my system, it's not to say that you can't have two objects within your system swapping energy, because actually that's the first sort of problem we're going to run up against here in a minute. Okay? But it's closed to the surroundings. So this is a classic sort of problem. And you've got, and I don't know if we'll get through part 3 also. We'll definitely start part 3. But at the end of part 2, you've got 4 problems that this is basically the scenario. And it looks like this. Oh, I need to remind you, you guys did some homework and handed in for me. And you guys use this, Q, change in energy. I've been saying thermal energy, but it just should be change in energy. Change in energy is equal to, if you can observe a change in temperature, then the change in energy is equal to MC sub P, which you look up on a table, specific heat, delta T. And delta T is the change in temperature. And one of the things before your test we talked about is delta T. Anytime you see a delta, always means change in. And it's always going to be final minus initial. So in this case, it's T sub F minus T sub I. Final minus initial. Okay, so in this case, we have an aluminum. We have small bits of aluminum. Let's go with, I'll make my little, this is my chunks of aluminum. I'll go ahead and label it AL. Al. Okay. And I'm going to go ahead and pick out the M of aluminum, C sub P of aluminum, and the initial temperature of aluminum, and the final temperature of aluminum. Now, I'm a firm believer in working problems so someone else can follow your logic. So kind of quickly, if we just use little subscripts here, then actually we can keep track of what's what. We can also do a little picture here to kind of keep track of what's what. Okay, so notice right off the bat, unknown mass. Like, dang it. Okay, so mass of aluminum, question mark. All right. Specific heat of aluminum. Hey, I got that. Okay, so 0.902. Specific heat are units of joules per gram degrees Celsius. I know it's written as J/G/degrees Celsius, but just go with me. That's really what it means. Okay, now it says that it was heated to 98.7 degrees. So actually, that's going to be my initial temperature. 98, sounds like a good FM station, yeah. What's that? Initial. Yep, that's initial. Yep, it's heated. Yeah, and I haven't shown you why that's initial, but I'm going to show you here in a minute. I've read the problem a few times, and then if you read the problem a few times, it says, okay, somewhere else outside of the system, this aluminum was heated, and it was heated to 98.7 degrees Celsius. Now, here's where the system comes in. It says that that aluminum was immersed. Immersed means plopped into. So it's immersed into water. So actually, over here, I'm going to draw my famous beaker. And this, of course, is going to be my water. Okay. So I am going to, after I heat it up to the 98.7 degrees, I'm going to douse it in my water. Now, what do we know about water? Well, it goes ahead and it gives us the mass of the water. So I'm going to put M sub water is equal to 50.0 grams. Okay, specific heat of water, do we know that? Yes, I'm just going to put a check mark there. That's that 4.184, it's not writing. 4.184, it's catching up. Joules per gram degrees Celsius. I'll go ahead and write it. 4.184 joules per gram degrees Celsius. Come on, catch up with me. But you see how basically I'm going to, when I take that solid aluminum and put it in my water, basically now I have a system of water and aluminum. That is going to be my system when I work problems. It's reconnecting. Come on, you can do it. I know it's Monday, but come on.
And then technology died.
It should be okay. There's my little hotspot. You can do it. How long do we do it? 1001, 1002. Oh, jar, evil. Last time. Not bad. Okay. So, as I was saying, specific heat of water is that 4.184. See how it's like very symmetrical. Joules per gram degrees Celsius. This will make more sense when we kind of work the problem. Let's see, can we come up with an initial temperature of the water? Everybody see it?
22.2.
22.2 degrees Celsius. Okay, now, here's the deal. I'm going to go ahead and draw my little aluminum over here. Okay, that's my aluminum. I have a heterogeneous mixture. Okay. Now, we have a common equilibrium temperature. Actually, the common temperature when the dust finally settles, equilibrium temperature, 33.3 degrees Celsius. That is both the final temperature of the water, so T sub F of water, 33.3 degrees Celsius. So it went up. That makes sense, right? And the final temperature of the aluminum is also 33.3 degrees Celsius. Is that not awesome or what? So basically the aluminum cools down, the water heats up. All within our system. So here, let me just draw a box around. That is our system. And no, the aluminum probably will not float, but you get the idea. So to work this problem, it's kind of like your titration problems a little bit. Well, maybe not. Let's just go on to the next slide. Okay, so here's the deal. Your system is isolated. What was the system? The beaker with water and ultimately the aluminum in it. Okay, now it might not be a beaker. When we do this lab, in the chem lab, we use like a coffee cup, styrofoam cup. Oftentimes the cup we're going to use is oftentimes called a bomb or a calorimeter, as in calories, calorimeter. Okay. Assuming it's isolated. If it's isolated with regard to both mass, you figure no mass is going to get out of the beaker, but energy could get out of the beaker. If you held the beaker and it felt warm, energy's getting out. We're going to pretend it doesn't get out. Okay. Sometimes when and I'll try to kind of show you a problem like this, but sometimes we do take into consideration the energy that the container itself absorbs. But we're going to neglect that for now. If that's the case, then as our aluminum cooled down, okay, and our water heated up, we can make these broad statements. Okay, so I'm going to go ahead and show you the beaker again. Here's our beaker. Here's our water. We'll make them green now. Here's our chunks of aluminum. They aren't floating, but just bear with me. Okay, so that is our system. Okay, all of the energy that's gained by the water, because we saw it heat up, was energy that was lost by the aluminum. Okay, in other words, all of the energy lost by the aluminum was picked up by the water. It's a wash. Okay, that's important in this sort of problem. So then, with that in mind, and again, it's about subscripts. When I grade stuff, like on a test or on your homework, I'm actually looking for these little subscripts because I'm going to show you here in a minute. We do have we have changes in energy. We actually have 3 Qs. We have 3 changes in thermal energy. But as long as it's isolated, the change in thermal energy of the system, which is the beaker of water and the beaker of water with aluminum, it's 0. But within the beaker, we definitely have things swapping energy. Okay? What are swapping energy? Well, the aluminum is losing energy, and the water is gaining energy. So I'm going to put lose and gain. So remember when we talked this first lecture on thermodynamics, we said that you could have negative Qs and positive Qs? That's where we're going with this. Okay. So we can, since the change in thermal energy of the system is actually 2 things swapping heat, change in thermal energy of aluminum plus the change in thermal energy of the water. And since the change in thermal energy of the system is equal to 0, then the sum of the change in thermal energy of the aluminum plus the change in thermal energy of the water is equal to 0. So we can rearrange this. Now sometimes you'll be working problems, and I'll warn you that actually you'll have a 3rd or even a 4th term, a 4th Q term, or something that's going on within your system. This case is pretty simple. We only have 2 things in our system that's happening. So we can rearrange that. Okay, and we can actually then say that the Q of the aluminum is equal to negative Q of the water, just by subtracting Q of water from both sides. That works. So what, they're going to be equal in magnitude, but opposite in sign sort of deal? So if you go back a few slides, if you guys made that diagram that I did of the problem, do you see where basically you have everything you know? On the water side, you basically have everything you know to knock out a Q. Okay? And then you're going to find that. Okay, I have one more thing to say. Okay, so in other words, Q of the water is equal to negative Q of the aluminum. Now, I will be looking for these when you work your problems, like I said, on your homework or on your test. You know, communicate to me how you're working your problems. Sometimes students skip this step. So what I started to say, yeah, this is even better. You can knock out Q of water, okay? And then once you have Q of water, you know that you'll know Q of aluminum. Okay, and then if you look on the aluminum side, what we were after was mass. So we know Q is equal to M, C sub P delta T. We know C sub P for aluminum. We know delta T for aluminum. We can solve for mass. That's basically how we're going to work this. The problem about these problems is that if you look at all kind of the things Q is equal to M, C sub P delta T, any one of those variables can be gone, what you're solving for. So they kind of take on kind of different variations. Okay, so back to the original problem we've been working. Like I said, with regard to the water, we know the mass of the water, 50.0 grams. We know, and if I don't give it to you on the test or whatever, you know for liquid water, the specific heat is 4.184 joules per gram degrees Celsius. Feel free to rewrite this 4.184 J over G degrees Celsius. And we were given, and sometimes the initial temperature and the final temperatures, that's where it gets a little tricky too. You have to read it a few times if you're like me. So the initial temperature, or the final temperature of the water was that one equilibrium temperature, 33.3 degrees Celsius. The initial temperature of the water was 22.2 degrees Celsius. This is also where sometimes I'll say me, I won't just say students, we get our finals and our initials mixed up, but it's always final minus initial. So in this case, it's the equilibrium temperature minus initial temperature. So we do get a positive Q. Okay, which we'll get a positive delta T, which gives us a positive Q. Okay, and that's what we're going to see is that this is the water. Anything that's sucking up energy is going to have a positive Q. The Q is going to be greater than 0. All right, cool. Well, we said the next thing was to go ahead, well, I guess we need to plug that into our Q is equal to M C sub P delta T. Okay, so you notice that I knocked out delta T on the previous slide. Don't forget to show me that little, say, dippy calculation, that subtraction calculation. For two reasons. One is if you make a mistake, I can track it back to your delta T, and the other is it's just the right thing to do. Okay. So Q is equal to M, 50.0 grams over 1, times C sub P, which is 4.184 joules per gram degrees Celsius, times delta T, which is that 11.1 degrees Celsius. And I showed you this the other day, but do you see how grams cancel, degrees Celsius cancel, and we're left with units of joules, which is units of Q. So that's awesome. Looking like 3 significant figures. Okay, so 2.32 times 10 to the third joules. Now this is where sometimes students say, well, could I have written as 2,320 joules? Yes, because that would give you 3 significant figures.
Just don't put a decimal at the end.
Just don't put a decimal at the end because that would give you 4. And last time when we were here, we kind of talked about oftentimes units of energy, they wrap it up into kilojoules instead of joules. And I'll kind of leave that to your discretion. There are times when it's going to be easier if you go with kilojoules. Okay? All right, so now remember the next step then is to go to the Q of the aluminum. So the Q of the aluminum is equal to negative Q of water. So Q of aluminum is equal to negative 2.32 times 10 to the third joules. And this is a very much a pattern. You know Q, you know everything to get Q of one thing, and then you don't know one thing of the other. And they're just swap and eat. Okay, so now what I usually do is rearrange Q is equal to M C sub P delta T. I rearrange it, in this case solving for M. So what I'm going to do on both sides of the equation is divide by C sub P delta T. And if I do that, I get M by itself is equal to Q of the aluminum divided by C sub P delta T. And like I said the other day, this looks very much like a physics thing, you just plug and chug. But in chemistry, and it should be in physics too, you have to include your units. Okay, so here we go. So what do we know? This is all about the aluminum. And I wish I had like little subscripts here, but I guess if I said Q of aluminum, then I guess that would be okay. But that's all the things we know about aluminum. We know the Q now. The specific heat was given in the problem, and you get that from a table. Specific heat of aluminum is 0.902 joules per gram degree Celsius. And the delta T, it's always final temperature minus initial temperature. And it's classic that actually you have an equilibrium temperature that something has cooled down to and something has heated up to. Okay, so the final temperature is at 33.3 degrees Celsius. The initial temperature was the temperature of the oven or whatever that this thing came out of, the 98.7 degrees Celsius. So if we're careful about T sub F minus T sub I, we definitely have a negative delta T here. And it's the sign of your delta T that drives your Q, because your mass can't be always, your mass is always positive, your specific heat's always positive. Okay, so we have a negative Q, and that actually is a situation where something's giving up energy. All right, so plugging in to find the mass of the aluminum, again, I would, I'm getting a little sloppy here, mass of aluminum, okay, mass of aluminum is equal to the Q of the change in thermal energy of the aluminum, negative 2.32 times 10 to the third joules, divided by the specific heat, 0.902 joules per gram degree Celsius. Also in the denominator, the delta T, which is negative 65.4 degrees Celsius. And we've been all about seeing what cancels. This is a little bit more interesting. So joules in the numerator cancel with joules in the denominator. So in the denominator, we have degrees Celsius and grams degrees Celsius. So I bet you by this that this degree Celsius cancels with this degree Celsius. Now what we have in the denominator basically is 1 over grams. Okay, that's our units. Now, I'm not a math person, but if you have something in the denominator like this and you want to bring it up, basically if you flip it, you can. So this thing actually simplifies into grams. All right, so that's the units. We need to round to 3 significant figures. So the mass must be 39.4 grams. And that's it. So a lot of numbers, but I think it's cool that, no pun intended, that you can, watch how the behavior of the system to calculate the mass of the heated solid. Okay. So these will be due on Wednesday. So I didn't push out my other ones, did I? Oh well, you guys must not have needed them, or somebody would have squawked, I guess. I wasn't on purpose, because I was doing these. I'm like, I never did that. But it was a blur Thursday. It really was. Well, that was Wednesday. Okay. So 4, 5, 6, 7. There's a picture for each one of these. And sometimes I don't know how much these all really help. It's kind of a mixed bag. Does this help? I don't know. Will I stop doing it? Probably not for this semester anyway. So here's a picture. If you read the problem a few times, you'll see that there's silver, Ag, and then there's a bucket of water waiting for it. Notice that, like I said, it's classic in that the question mark is with regard to the specific heat of silver. Can you look that up? Yes. Should you or could you? Yeah, you can see if you got the answer right. Okay. But in this case, actually, with regard to the water, notice they came to the same equilibrium temperature, just like we saw before, and they give everything. Okay, so my hint then is basically, you know, I remind you that in this problem, basically you have an isolated system, and you have two things swapping energy. You have the silver and the water, okay? And so you know more about the water. Go ahead and knock out the Q for the water, okay? And then that will give you the Q for the silver. Rearrange the Q is equal to MC sub P delta T to solve for C sub P of the silver. And that should work just great. And then this one, I mean, do you see a theme? Again, it takes me a few times. If it takes you a few times to come up with a picture, you're in good company, because it does me. So in this case, we have iron instead of silver. Okay, but again, we have a little vat of water over there. Notice the question mark here is the initial temperature of the iron. So they give you this common equilibrium temperature, is very common, okay? Again, we know more about the water, so to work this, the first thing we're going to do is go with the change in thermal energy of the water, okay? Then we're going to go ahead and get to the change in thermal energy of the iron with this relationship. Okay, now you have 3 and 4 down here. You actually have a couple ways of skinning this cat. What I like to do is go ahead and calculate delta T. Okay, Q is equal to M C sub P delta T. By that time, you know everything except for delta T for the iron. I leave it as an entity, and then I go ahead and calculate the initial temperature once I get delta T, knowing that delta T is equal to T sub F minus T sub I. Okay, then I will know this, and it looks like I know the final temperature. Okay, that's how I do it. You could do it another way. Okay, next one. That is my stainless steel. Okay, SS for stainless steel, that's our solid. Notice we're trying to get to the mass of the stainless steel. It's similar to what we did before. And in this case, I guess the only catch is they don't give you the mass of the water directly. They give you the volume. Okay, and actually they don't even give you the density. But you know the density of water? Yeah, and they're going to need to use that with the volume to get the mass of the water. And the specific heat of water, that's the one you need to memorize. So it's very similar. And then the last one, this is copper. Let's see, what don't we know? We know lots of stuff. Wow, we know everything about the copper. Now it's not water this time, it's glycerol. They give you the volume and the density of glycerol, so you have to get the mass of glycerol. Notice what we're after is the specific heat of glycerol. So you're going to start over here this time. Yep. Go specific heat, or excuse me, go to the change in thermal energy of the glycerol, Q of the glycerol, rearrange it to fall in specific heat, plug in. That's what I would do. Okay? They're fun. But I just think it's easier if you, I like the pictures, and I like the subscripts. So, but you don't have to do that. Yes, sir. Somehow show you work. Okay. Dun, dun, dun. Still with thermodynamics. Still with basically, it's weird to think that you're tracking energy because you don't really see energy, but we can, if it changes temperature, we can look at that, okay? So I think we've talked about endothermic and exothermic before. I know you've probably run into it in other places other than this class, but let's kind of revisit that. In light of the idea we talked about a system, which could be our beaker, the boundary, which could be, or I guess I should say the system would be inside the beaker, the boundary would be the beaker itself, and then the surroundings would be anything else up there, okay? So an endothermic process, okay, is one in which within the system is taking energy in. I like endo and in, okay, it's taking energy in. Now, if something's taking energy in and we're tracking its temperature, okay, if the energy it takes in does do something with this temperature, this temperature's going to increase. So your final temperature is going to be higher than your initial temperature. Your delta T and Q is equal to MC sub P. Delta T will be positive. That means your Q will be positive. That's all consistent with this. Q of your system for an endothermic process will be positive, greater than 0. All right. Exothermic. Oh, I guess here's a picture of an endothermic. So one of the things we're gonna be talking about are phase changes. Okay, so if you want to melt ice, basically you give it some heat. Okay, give it some energy. Okay, and that's what's being shown here. It's an endothermic phase change. So if we were to kind of draw little system isolated by a boundary from its surroundings, this is kind of what it looks like. Basically, from the surroundings, energy is going into the system. From the surroundings into the system. Endothermic process. Exothermic, energy is going to be released. Okay, exiting. Okay, what's it going to be released from and to? Well, it's going to be released from the system to the surroundings. Okay. I just now thought about these. These would require that your boundary doesn't isolate your system from the surroundings, isn't it? Make sense? It's not just staying within your system, it's crossing the boundary to go into the surroundings, or it's crossing from the surroundings into your system, past the boundary. All right, so an example of something that's exothermic might look like this. Basically, that picture's trying to show you is, I wouldn't want to put my hand around it, but if you were to put your hand around it, odds are it would be hot, warm. Okay, so the glass doesn't isolate the energy. The energy is crossing the glass into your hand. Okay, and your hand would be part of the surrounding. So exothermic. Now, if something's exothermic, its final temperature is greater than its initial temperature. Wait. No, it's not. Well, it's no. Check that. Exothermic. This isn't a good analogy. Okay. I have two new variables for you. Q is change in energy of the system. Okay. W is work done either by the system on the surroundings, or work can be done by the surroundings on your system. And delta of course is change in, and U is the overall energy, internal energy of the system. So basically what we're saying was happening in your system, it's got two things going on. It's your energy and it's the work that is done to or done by your system. So of course it's all about positives and negatives. All about positives and negatives. We said that if heat is added to the system, that's an endothermic process. We said Q is positive. And we said, well, now we're saying, if you take your surroundings, and if you take from your surroundings and you do work on your system, okay, then actually that's going to be a positive W for your system. So in other words, of course, greater than 0 means positive. Greater than 0 means positive. So all this is saying is if I have a positive Q, means energy is being added to my system from the surroundings, might I add. And a positive W means work is being done on my system from the surroundings. This has got to be positive, doesn't it? What makes it interesting sometimes is if you have one positive, one negative, then you're like, I don't know what delta U will be. It depends which one's bigger. Okay. But and I have some pictures coming up, but as we talk about this, just remember that this would be my beaker, put the system, and then anything out here would be my surroundings. Okay, so here's my picture that basically says it all. So this is the change in internal energy, delta U, of the system is equal to the change in energy of the system plus the work done either on the system or by the system. So here are some possibilities. They're kind of just rehashing what we talked about. Endothermic, we said be a positive Q for the system. And so anything outside that yellow box is the surroundings. Inside the yellow box is the system. That's kind of how this figure is working. Okay. The exothermic, we said that that would be heat or thermal energy leaving the system, going into the surroundings. That's a negative Q. And here's our W's. Okay. If the surroundings does what we say work on the system, that's a positive W for the system. If, and I have just one example here at the end to show you, if your system somehow does work, it's going to do work on the surroundings. And actually, that's going to be a negative W for the system. That kind of makes sense. Okay. So another variable, this is the third new variable today. We've got the delta U, we got the W term. But between the delta U is going to go away, the change in internal energy, leave that for physics. And the work term, we'll leave that for physics too, although you need to know a little bit about it. This term is here to stay for chemistry. Enthalpy. And one of these days I need to look up why, oh why, oh why. I need to look up a lot of things. But why is the symbol for enthalpy H? I do not know. I bet it's Latin. I don't know. So enthalpy, not to be confused with later on entropy. We've all probably more heard of entropy than enthalpy. But enthalpy, if your experiment or process, if it is occurring at a constant pressure, which just means like in the lab, basically the pressure remains the same. We're not pressurizing your vessels, nor are we pulling a vacuum on your vessels, so it is at constant pressure. If that's the case, then actually our energy terms, and here in a minute, okay, our Q, actually, these are going to be synonymous. So it's hard to get a fix on enthalpy, but it's much easier to get a fix on change in enthalpy. Gotta keep me, what's that? Keep me honest, or what is, can't remember what that guy calls it. Delta H, change in enthalpy. Okay, so like I said, we mostly look at changes in enthalpy. We look at the initial enthalpy and the final enthalpy and changes in enthalpy. So like I said, if it's done at constant pressure, which is basically all that we do, then the delta H, change in enthalpy, is equal to Q, change in energy. And anytime you see a delta, just like temperatures, deltas are always final minus initial. I couldn't think of where, but I thought we talked about state functions versus path-dependent functions. Not yet. So a state function or state property, a state phenomenon, a state function, just simply means that you get an initial, like your delta H. You need an initial delta H and a final delta H. Okay, it's always final minus initial. Okay, but you basically know where you started and where you ended, but you don't care about the path in between. Okay, that's a state function. It's what we call path independent. So state function is equal to independent of path, independent. And I've heard it likened to like your bank account. Like, you know how you have, at the beginning of the month, you have an initial amount balance, and at the end of the month, you have a final balance. And you can get the change in balance for the month. And it doesn't matter if you put $1 million in there and took out 500,000 and then took out 250,000 and then basically took out, all but $1, okay? You end up with the same, or you added some in and took some out, added some in, took some out. It doesn't matter. Okay, it just depends on the initial and the final state. Okay. So now the only difference here with the delta U, the change in internal energy, is the Q term. The Q term has been swapped out, and the delta H, the change in enthalpy term, has been swapped in. That's it. So here's the deal. If work, the whole W term, like if you're like, hey, my system really didn't do any work, okay, on the surroundings, nor did the surroundings do any work on my system, if that W term is basically 0, then your delta U, your change in internal energy, is approximately equal to your change in enthalpy. Makes sense. If it's basically 0, you guys are familiar with those means absolute value, okay? Or if basically the absolute value of the work term is so much less than the change in enthalpy, delta H, and you're like, yeah, it's negligible. So the one picture I have for you is kind of weird. That little granular thing right there is actually dry ice, carbon dioxide. So carbon dioxide, she really should not be holding that with her bare hands, because, yeah, it's like, whoop. But anyway, it's funny because they show some videos where I'm like, really, gloves, you know? But anyway, one thing about dry ice is it sublimes. It goes straight from being a solid to being a gas. So all they're doing basically is putting that dry ice, which is carbon dioxide solid, into a Ziploc bag, and then they close it, okay? And then they make the system, which is the Ziploc bag with the carbon dioxide, changing from a solid into a gas. Of course, as a gas, it occupies more volume. So basically, it expands, and the work it's doing is lifting up the book. Yeah, there you go. So in this case, actually, our work term would be, what, negative? Because the system's actually doing work on something in the surroundings.
Gravity.
Yeah, the book is part of the surroundings,
Yeah.
right? Yeah. So the homework then, that's due, looks like this. That's also due on Wednesday. And I'll show you what that looks like. $7.55. So there's two problems, and they're a little bit different. I went ahead, and this is a nice little figure from your textbook, the two yellow circles. And all it's doing is kind of what we talked about. Kind of on the left, you see the system. Basically, it's an exothermic reaction, a reaction or process, because it's releasing energy, negative Q. Notice actually it must be doing work from the system to the surroundings, makes a negative W. That's like the book we saw, okay? The book was being lifted. That's the work being done by the system on the surroundings. The book's part of the surroundings. Over here we have kind of the opposite, okay? We have an endothermic reaction, Q going in, okay? And we have that work is being done on the system by the surroundings, okay? So then I just actually gave you some hints through A through C. They're just like quick little math problems where you subtract one from the other. Or I guess I should say more appropriately, you add the Q and the W term. The catch is the Q positive or negative? And I've kind of gone ahead and told you what they are. The next one is just kind of a little interesting. In this one, in contrast to the other one, basically it says, what is the change in internal energy of the system if the surroundings does the following? Then it tells you A, B, and C. What are the surroundings doing? So if you're like me, you just have to read it a few times in context of what we just talked about. Okay, so for instance, A says the surroundings is transferring 2.35 joules of heat. Now, okay, so the surroundings is transferring it to what? Well, the surroundings must be transferring it to the system. Okay, so that's an example of an endothermic process. So that's, you see under Q, I said that must be for the system. That's positive. Okay, so I kind of did that for each one of them. I tried to kind of color code them. I love colors. Okay, so it is a little bit different, and I'll just kind of leave you to that and we'll let over. Very good.